Hey everybody, let's get started. I'm Glenn Poirier. I work with Paula at the Canadian Museum of Nature. I'm a senior research assistant there. And I've also got a secondment to this lab here at the University of Ottawa. I run the equipment for the lab for the university, and we look after all the museum stuff, work with students, and it's a good place to work. So we're going to try something different. I've never done an unlive lecture before. We're going to do some actual moving around the camera, so audio visuals may not be perfect. Bear with me. Should be fun though. I'm glad to see we got 38 people, including Mom. Hi, Mom. So yeah, I'm going to get started. What I want to talk to you today is how electron microscopy, specifically SEM, EDS, and microprobe, can be applied to mineralogy and mineral collection. And 10 years ago, I would have given you a completely different talk and told you, SEM, EDS, don't even bother. If you need numbers, go to the probe. But the state of software, the state of the instrumental analysis equipment, things like that, have really, really improved over the past 10 to 15 years. And we can get some really interesting and nice data with a scanning electron microscope, which is available to a lot more people than a microprobe. Microprobes, I think right now, there are about 7 or 8 equipments. There are 8 in labs across Canada, mostly associated with universities. It can be very tricky to get access to the machines if you're not associated with a museum or something like that. So I want to talk to you about what they do, why they're different, what they can do for us as mineralogists and mineral collectors. And so let's get started. Here I'm gonna change screens around a lot, so if it stops for a second, don't worry. And I've got Paula on the phone here too, so she'll telephone me if things go terribly wrong. There. Okay, so now I'll just show you the lab. I'm just going to show you the lab. So what we're looking at right now is our JEOL scanning electron microscope. Okay, I'm sorry, JEOL microprobe. I know better than that. This is the machine that the lab has been built around. It was installed in about 2011. It's fully automated, great machine. We do a lot of really interesting work with it. And just slowly scanning around the lab. So we've got a really nice lab here. It's the first time I've been in a lab that has actually been designed for scanning electron microscopy. Hang on a second. This instrument here is our scanning electron microscope. This is a Joule 6610 LV, and it arrived at the same time as the microprobe, and it's used a lot, as almost as much as a microprobe is in a lot of times. And so the rest of the lab, I've got a pretty well set up lab. I've got sample preparation over there with my polishing and cleaning areas. I've got lots of storage space. It's filling up. I've got my sample prep areas. I've got a couple of really good research grade microscopes, different types of good cameras. I have a CL microscope, cathodoluminescence microscope with a spectrophotometer on it. So we're really well set up. The lab is sitting on a pad. I don't know if you can see it here. It's sitting, you can see the marks on the floor. The lab is sitting on a pad that's separated from the rest of the building, and it's actually attached to the bedrock about 40 feet below me by pilings. So we are isolated from all the rest of the buildings in terms of vibration. So it really makes this place a beautiful place to work. Temperature control, we are set so the lab doesn't vary between any more than 0.1 degrees centigrade over any 24-hour period. So that's the lab. And so let's talk about electron microscopy first. Just a little bit about microscopy. All right, so the lab, it's called Probe versus SEM, but they're actually very complementary in what they can do for us. myself straightened up here. So again, these are the two instruments. So they're designed for different things. The SEM is designed as an instrument for imaging primarily, and what we use as mineralogists, we add a EDS detector to it so we can look at X-rays coming from minerals, and I'll talk a bit more about that later. But it's designed mainly in this lab here, it works mainly as a survey instrument. We put things in the scanning electron microscope, figure out what they are, what their relationships are, what their textures are, and if we need to, then we can go to the microprobe and actually collect real data, going to collect more accurate data. The probe, as I said, is designed to be a reliable, accurate instrument for collecting precise compositional data from a very tiny area, down as low as 10 microns, although in practice we often go larger. And it's still the only instrument that can do this. There are all kinds, laser ablation mass spectroscopes are great at doing trace elements, but you can't do major elements with them. Same as SIMs, again, these are fine for trace elements for small areas, but there is no one instrument that can do good quantitative analysis of major, minor, and trace elements the way the probe can. So what do they have in common? These two machines are both based on scanning electron microscopes. They've got electron sources. They have magnetic lenses that focus that electron beam down to a point on the sample. They've got electron detectors, which is how we get our image, and we'll talk a bit more about that. And they both have EDS detectors. Even the microprobe has one of these. I'll show you. Yeah, you can see that. This is a different type of X-ray detector. We have two different X-ray detectors on the probe, and I'll talk a bit more about those later. So from that perspective, they're very similar machines. They've both been optimized for certain things. As I said, the probe is optimized for quantitative data, and the SEM is actually optimized for ease of use. This is a very great machine to use. This we will talk a little bit about. Oops, sorry. Yeah. Let's try there. So this is a generalized SEM column. Only thing you got to know is that we've got an electron source up here, which looks a lot like a light bulb. It's a tungsten wire to a point. We heat that up to about 2700 Kelvin, put it in a strong potential field, and we can draw electrons off that. Electrons are negatively charged, so in a magnetic field, we can focus those beams. So we use a couple of lenses coming down the column to focus that beam to a point where the sample is. So we want a very fine point where the beam impinges on the sample. And then we have scan coils, which is how we form an image, and I'll talk a bit about that more in a second. So that's basically the very common things. Both of these instruments also have vacuum systems because we have to work in a vacuum. Electrons won't make it down the column if it's full of air, right? The air will just stop all the electrons. So we need to have a fairly decent vacuum in the chamber of these things. They're both under vacuum. I'll skip that. So image formation, how do we form an image in these things? They're not like optical microscopes where we're seeing through a sample, or we're not looking at light reflected off a sample as in the case of an ocular microscope. What we're doing is we're actually taking the beam, and we have scan coils, and we are rastering the sample back and forth, or the beam back and forth in that sample. So every pixel, every point on that sample gets rastered back and forth. And for every point on that, we look at the electrons that come back from that point. We throw that up on a screen, and with a number of electrons corresponding to how bright that pixel is. So if we take a beam, we're rastering an area that's about, let's say, 10 microns by 10 microns square, small square, and we throw that up onto our screen, which our screen is now probably 30 centimeters by 30 centimeters. That 30 centimeters over the 10 microns, that's the actual magnification. That's how we get our magnification. We take a very small raster and transfer it to a big screen. That's our magnification. So we're looking at the electrons coming off of these samples. So we've got, recently I have a new microscope and the situation's become a lot more complicated, but essentially we have two main types of electron detectors. We have what are called secondary electron detectors and what are called backscatter electrons. And secondary electrons are low energy electrons that come off of that sample. They impart a lot of energy, they lose a lot of energy in the sample. And then backscatter electrons are electrons that come off the sample with almost the same energy as the beam. And what are they? They show us two very different but very complementary things. And this is just a picture of what the situation looks like in my instrument now. The beam comes, this is looking up the column. The beam will come out of that hole there. This detector around that hole is a backscatter detector. And this detector back here is a secondary electron detector. And this is the X-ray detector here, and we'll talk about that a bit later. I'm going over a lot of the details here because we don't really need that for what I want to talk about you guys about today. So how does the secondary electron detector work? Secondary electron detector looks at the sample from an angle. It's got a wire cage around the end with a positive bias. So it's charged to be a positive bias on that cage. So positive bias will attract low energy electrons, which have a negative bias. So they'll pull those electrons into the detector. So what do we see with that type of detector? If you look at this picture here, you can see this area here is bright and the areas down here are not so bright. What that means, the detector is looking at that sample, which is your dendrite from Mont Saint-Hilaire, one of the pictures Bob and I took for the book. The detector is here and it's seeing that areas that are facing towards that detector are brighter, whereas areas that are not directly pointed at that detector are darker. What this does is it gives us a really, really good sense of topography. We can really get a good idea for the surfaces and the features of that area. So you can see how well this shows up the individual crystals of dendrite there. The other one that we tend to, as mineralogists and geologists, often makes is more informational to us, is a backscatter detector. And the backscatter detector works on the principle that minerals or materials that have a higher average atomic number produce more backscattered electrons. Okay? So if I have, for example, a piece of quartz and a piece of hematite next to one another, the hematite has a much higher average atomic number. And so in a backscattered image, that will appear much brighter than the quartz, which is a lower average atomic number. And this image here is a britholite, and it's one of the first images I took with this SEM. And what we were looking at, we can see some fine zoning in that britholite sample. And what we're seeing in that zoning is some very minor differences in the concentration of rare earth elements, which are quite heavy. So minor changes in the concentrations of rare earth elements will show up very well on the backscatter image. So we're seeing zoning caused by when that sample was growing and incorporating more or less amounts of excuse me, rare earth elements. The bright area here is a thorium-rich mineral, and because thorium is really heavy, we have a very bright image there. So you can see how this is really useful. By looking at a thin section, if I'm looking at a particular piece of rock in that machine, the backscatter detector can really tell me a lot about mineralogy just by a quick look at that image. Okay, let's try some live stuff. Let's go look at the SEM. And so what we're going to talk about now is when is the scanning electron microscope the best tool for the job? Then, I am keep the screen, hang on a second. Oops. The SEM is a great tool for surveying when we've got samples that are rough and irregular, when we've got samples that we haven't been able to pull apart and we can't polish. It's a pretty good, it's a good tool for general survey work and a lot of actual good final work because it's very flexible. One of the things in this particular machine that makes it very flexible is that it's got an enormous sample chamber. Here, hang on a second. I'll shoot. Hopefully nobody gets this. No, sorry, can't do that. Never mind. Yeah, anyway, it's got an enormous sample chamber, which means that we can put very irregular samples into this chamber. We have cameraman here is what I need, but anyway. There. Right. Yeah, so we have a very large chamber and we can put big irregular samples in there like this particular piece of feldspar. Okay, so we can put large samples in. And one of the things we need to talk about before we do electron microscopy is the fact that our samples aren't conductive. In mineralogy, unless you're looking at native gold crystals or maybe native copper, our samples do not conduct electricity. So we take an electron beam and fire it at a material that's a conductor or at best a semiconductor. We are going to build up big negative charge in that sample. So we have an electron beam coming down, trying to hit the sample, but it sees a big negative charge and it's going to want to scoot off to the side to avoid that negative charge, which is not good for stable imaging. So what we often need to do with electron microscopes, and previously that was the only choice you had, was to carbon coat or to coat your sample with a thin film of a conductor like carbon or gold, which is nice if you can do it. But I work at a museum and a lot of the material we work with, we're not going to be able to put any kind of sample prep into it. We can't carbon coat it, we can't gold coat it, because these are not removable coatings. So for museum pieces or for valuable mineral pieces, this is not a real option. So how do we get around this? We can do that in a couple of ways. We can do low voltage imaging, okay? The assumption behind this is that if the voltage is low enough, the sample can discharge by itself. It can dissipate all that electrical charge on its own. And so we just don't charge. And that's great. Really good way to look at material like butterfly wings or biological material that we don't want to coat. And it's a nice gentle way to look at these things. Problem is when we're looking at minerals, we don't get good backscatter images with that low voltage. And secondly, B, with low voltage like that, we're not going to generate X-rays, which we'll talk about later. We can't generate X-rays. We need a much higher beam energy to generate X-rays. So for most of our mineral stuff we do with minerals, we use what's called a low vacuum mode. And it's really simple. All we do is we put about 30 pascals of air, very low pressure of air into there. And that air is just capable of dissipating the charge away from that sample area. It's not perfect, and I'll explain why when we start talking about X-rays, but it means that we can look at samples without putting a carbon coat on, or without and potentially damaging them. Okay, so it's still a bit of live work. I'm not sure how much you'll see of this, but this is a piece of a feldspar crystal from a pegmatite pocket in Takeo in Cambodia, where Paul and I and some of our colleagues were working in February. And you can't see it in the camera, but on the surface, it's got a really fine late growth of feldspar crystals growing on it. Nice white crystals. So we'll put that in the machine. And I'll close the door. One of the things with microscopes is we have to be very careful. You've seen that picture of where the backscatter detector is on this machine, right above the sample. We don't want to hit that backscatter detector. That's one of the things I always on students there, is always making sure they know how high their sample is. Because if we touch that backscatter detector, everybody's having a bad day, okay? We have a single backscatter detector at our other microscope in the museum that, according to the salesman, is worth a fully equipped pickup truck. So whatever that means, I don't know, but they're expensive, and touching them destroys them. They're very fragile, so we really need to be careful. So a couple of things. I know the height of my sample. I know how high it is, so I've entered that in, so the machine knows not to go above a certain height. But I've also got, I'll show you in a second. Start pumping that down. And we've also got in our modern scope, we can take, there's an actual optical light camera in there. We can take a picture of the sample and use that to navigate around the sample. Okay. So I want to go look at, I've already looked at this morning, so I know exactly where I want to go. We've also got an infrared camera on this screen over here that shows us. Oh, okay. Yeah, the infrared camera here shows us a side view of the sample coming up, and it's an infrared light, so we can see the sample coming up and make sure that we don't actually touch anything in there. See the sample moving into position now. I pre-programmed this position earlier this morning because it's got some interesting features I wanted to look at for this. And we're just waiting for the vacuum to pump down. While we're waiting for that vacuum to pump down, I'm going to talk a little bit about X-rays. So the other thing that these SEMs are equipped with is an X-ray detector. So how do we generate X-rays? I'm not going to go into a lot of the physics of it, but essentially what happens is we got a high energy electron. It hits the electron shells of an atom in the sample. It knocks out an electron from one of the lower levels. Okay, say one of the K electrons from the lower energy level. Don't worry about these things. But obviously that electron cloud is no longer stable because it needs electrons in all those levels. So what happens is an electron from a higher energy level, like an L or an M, will drop down to fill that K shell. Okay, so because it's got a higher energy, as it drops down to that K, it's got to get rid of some of that energy. And what we're interested in is when it gets rid of that energy in the form of an X-ray photon. And the energy of that photon is very characteristic of where exactly it falls from and to. Okay, so if we get an electron in iron, say, that falls from the L shell to the K shell, it's going to emit an X-ray photon that's got an energy of 6.4 keV. Okay? I know this because I just realized today I've been working at this job for 30 years, actually, this week. But so 6.4 kilo electron volts. And so if we see an X-ray photon that's got that energy, we know it came from iron. So let's go back to our So this is what an X-ray spectrum coming off a sample looks like. We have all these different X-ray lines, and because we know for example, as I said, in an iron K-alpha X-ray has an energy of 6.4 keV, we can identify that line as iron. A nickel X-ray is at 7.5, somewhere around there. Copper is 5.4, or chromium is 5.4. And normally this is done now by the machine, okay? The machine will see an X-ray photon at that position and identify that line for you. But again, it's all going to be taken with a grain of salt. I had a grad student who should know have known better tell me that she had been looking at a technetium sulfide. And for those of you who don't know, technetium is actually extinct. There's none existing on the Earth, but it was, I think it was platinum. It was identifying a platinum peak as technetium. So you got to take these IDs with a grain of salt. Getting better and better all the time, but you got to take them with a grain of salt. So what information does this spectra give us? First of all, you can look at all these lines. This is some kind of weird nickel alloy. Look at all these lines and you can find out what elements are in there. But also important about that is that the intensity of these lines on the Y scale can give us some kind of information about the concentration of that element, how much of that element is there. So that's what we get. Oops. Okay. So one of the things that we're working with low vacuum mode, and that's very bad, very tricky to work around, is that we get what's called a beam skirt effect. An electron beam is coming down, and say 90% of that beam is actually landing on the sample in that point where we want it to land. But because we are working in an atmosphere, some of that beam gets scattered around that point. Okay? So we have maybe 10% of that beam, depends on the consideration, scattered around that point. And that beam's still got all that energy. So it's generating X-rays, not just where we think the beam is down, but generating X-rays in an area around that. And this is one of the biggest issues with using low vacuum mode in minerals. And I found a really good case when I was working last week. In this picture here, you can see this is it's a chromium bearing spinel. It's not a chrome spinel. You can see this chrome bearing spinel in olivine. This is a mantle xenolith. So this is porphyritic olivine with a crystal of chrome spinel, and that crystal is that crystal is about 200 microns across. And if you look at this probe, I was looking at that and I was finding silicon in the spinel, and I know silicon doesn't exist in the spinel. But even though I was taking an analysis point from the center of that chromite, I was still getting 3 to 5% silicon in that. And the reason is the beam skirt. The beam skirt, even though I'm looking at the beam directly in the center of that grain, the beam skirt is producing iron X-rays outside of that, in the olivine outside of that spinel, and they're being picked up by the detector as well. So this can be a really important, you really need to be aware of this when you're working in low vacuum modes. Okay? And just for comparison, I don't know if you can make it out, this line here, this blue line, I hope it's blue, is in a high vacuum mode with a carbon-coated sample, and you can see that in that chromite grain I get 0 silicon. So as soon as I cross the border into that chromite grain, 0 silicon. The beam influence with normal carbon-coated sample is about 2 microns, and that's all the area we're getting information from. With this beam skirt, we can get information from 100 microns away. We can bring in X-rays from 100 microns away. So this is one of the big problems with using low vacuum mode. And this is a polished sample, by the way, so that's another consideration. This is SEM. I just realized you didn't see any of those pictures I just showed you. Hang on a second. Sorry. There. This is what I meant to show you earlier. And again, I'll go over it. This is a spinel. This is the olivine. And so if you look at this, this is a profile of silicon as we cross from here to here. And you can see in the center of that grain, I'm still getting around 5 to 8% SiO2, even though, oops, even though we're 100 microns away from that boundary. So that's what I meant by the beam skirt effect. Okay, you can see here the beam skirt coming down, and you can see the influence here. So you're getting X-rays from a large area. Sorry about that. All right, let's go back. Yeah, somebody, Paula is texting me telling me that I screwed up. And so's my brother. Leave me alone, I'm talking. Okay, so SEM. So we've got that sample in the machine now. Yep, that's sample. Okay. So let's turn the beam on. Let's see what it looks like. So what we're seeing now is a whole pile of, I don't know how well you can see this, I'll try to explain it as well as I can. A whole pile of rough feldspar crystals sitting on this surface. Okay? And you can see the topography. You can also see some of these things are much brighter than others. And in particular, so you can see the crystals on the surface. You can see crystals growing on the surface. You can also see some backscatter effect as well. Some of these crystals, like you can see this very bright crystal here. You can see this crystal here. You can also see the surfaces, and you can see the feature on the surface that we scientifically call gunk, late stage slate gunk growing on crystals. So that's that sample we're looking at. So you can see there's a lot of topography on that sample. So this, when I'm working with EDS data, is what I consider to be our worst case scenario. When we have a rough sample, it's not carbon coated, it's not flat, okay? And this is the worst case scenario. Especially for imaging, it's great, gives you really nice, pretty pictures. You can see the very bright features there. Okay? So you can see that, but in terms of analysis, this is a very problematic situation. Let's take a look. So how do we do the EDS work? Is we'll acquire an image of that sample, and then we can just click on it to move the beam to where we want to analyze. So let's see what this nice big crystal is here. You probably won't be able to see it well, but so what I'm seeing now, the machine is acquiring that spectrum. You can see the X-ray lines coming up, and the machine is the software is automatically identified oxygen, sodium, aluminum, and silicon. And when I've seen enough albite in my life to know that the proportions of those peaks are what we're getting in albite, and that makes sense because we've seen a lot of late-stage Clevelandite kind of growth on this sample. Okay, so that's great. You know that. I don't think there's much question about that. We're looking at a big sample, and almost all the X-rays we're getting are coming off that surface. Okay. Let's just try something different, though. I want to see what happens if we do an analysis in a surface that's facing away from the X-ray detector. Just to show you the effect of geometry on the EDS detector. I'll take a second here. Okay, so now we got another one. And what I'm seeing, my eye is seeing, we're looking at a face that's pointing away from the detector, which means that a lot of the X-rays generated are not going to make it to that detector. They're going to be absorbed by the material in there. And what I'm seeing, I'll do that is that there's a lot less sodium, and that's the typical effect of absorption. The lighter X-rays will get absorbed preferentially by that sample. So the ratios of those peaks are no longer the same, even though it's the exact same mineral. So this is one of the things you got to be very aware of when you're doing EDS in these sort of conditions. Let's see if we can do a comparison. The other thing, you can't see it either, but the other thing I can tell from this is that the absolute number of X-ray counts is down by a factor of 10 looking at that surface. So one of the things you got to be aware of is where your detectors are. And then the other thing I wanted to show you is this very bright green here, which I still haven't identified. Very bright phase, and we'll see why it's bright in a second. It's bright because it contains 15 to 20% UO2, uranium dioxide. So it's uranium-bearing phase, makes it very bright, produces a huge amount of backscattered electrons. Problem is that all these grains are quite small. Like that grain is one of the bigger ones I've seen, is 30 microns. And what I'm trying to find out is whether or not this silica peak in there is actually part of that mineral. Because I always get a silica peak. And because of the beam skirt, I can't really tell. I could be looking at X-rays coming from the crystals around it, or they could be in there. After a lot of work on this sample, I've kind of started to realize that aluminum and silicon are always the same proportion, whereas phosphorus goes up and down. So it's making me think that the silicon is coming from the beam skirt. But you know, if I had only done one analysis of that, I would have assumed it was a silicon-bearing phase. I would have been really mistaken in my identification. And what you're seeing here this is a rare earth-bearing element too, and you can see all these rare earth peaks, and they're all smushed together, which is something we'll talk about in a bit later. So this is the worst-case scenario for this. I can, for some minerals, yeah, for the albites, I could identify the chlorides that grow on the surface are big enough. But when I'm looking at small phases like this, I have to be really careful that the X-rays I'm seeing are actually coming from this sample. And the geometrical effects as well. I had one of these crystals and I measured X-rays on one side and then the other. And the difference in phosphorus was 15 weight percent P2O5, depending on where I looked at it. So geometry as well. So doesn't matter. This is all really great stuff. You need to be careful about when you're looking at this type of data, when somebody shows you this data. You need to be a careful consumer of EDS data. You have to know how it was acquired, okay? Because what I'm going to show you next is what's been really nice about EDS in the past couple of years. What's the best case scenario? The best case scenario in EDS is when we've got a polished flat sample and that's carbon coated. Okay, and I had an opportunity just this week because I'm working on a project from the museum collection. A couple of years ago, one of our students, Ian Beats, sample all the tantalum columbite minerals, tantalite columbite minerals in the collection, because most of them are just as tantalite columbite. And to properly name them, you need chemical analysis. So he sampled all of those, mounted them up in epoxy blocks and polished them for me. And so for the past 3 weeks, I've been analyzing these things and getting names, finally getting names for some of these materials in the collection. I'll get you the data later, Erica. So what I had a chance to do was actually compare an analysis I'd just done in the microprobe with something I'd done with the SEM EDS on a flat polished surface. And not the best graph, but you can see the blue bars there are the actual results I got from the microprobe in terms of 100%. And then the actual crosses are percent different from what I got from the EDS. And I was very surprised and gratified to find that for major elements like niobium and tantalum, I'm within 2 or 3% on the EDS. This is just simply putting a beam on, letting the software figure out what the elements are, and doing an analysis. For minor elements like iron and manganese, I'm within maybe 10%, and these are minor quantities, so I'm in 5 to 10% for those. And titanium, even though titanium was half a weight percent, I'm still within 80% of that on the SEM. So I could have got a really good idea what the actual name of the sample was with a flat polished sample on the SEM. So if you don't have a probe, you can do this kind of stuff on the SEM. Pyrochlorers actually included pyrochlorers, and this is what I was really surprised at, how well the pyrochlor worked, considering that uranium and calcium and tantalum are all overlapped. They're not easy to separate these lines, and I was still able to get results within plus or minus 5 or 10% for most of the majors and minor elements. So, you know, the best case is you can do this really well. And if you don't have a probe, you can actually do quantified analysis on the SEM with standards, and you can get even closer to this. So, you know, SEM data, it's great, and it's a really useful tool. So, okay, why would I want to go to the microprobe then? What's the use case for doing microprobe work? This is just, again, some of that material I was just looking at, and you can see the red and the difference between the red and yellow spectra are just geometrical areas between the two of them. So when do we want to go to the microprobe? We go to the microprobe mainly when we want accurate data with a very good precision, or when we want to do trace elements. Yes, we didn't talk about it. I'll talk about it now. The SEM. I'll go back to those analyses. One of the things, if you look at this manganocolumbite analysis for zirconium and uranium, error is 100% or more, because uranium and zirconium are trace elements in the sample, and both of them are around 0.2 weight percent, ZrO2 and UO2. Okay, so 2,000 parts per million. And EDS, if you're very, very lucky, you might be able to see elements at a half a weight percent concentration. Below that, forget it. Whereas the probe, I wasn't even particularly looking for these elements at trace concentrations, and it still did a very good job of doing these concentration, of detecting them. How right those numbers are depends on how careful I was, but we can detect things at quite low concentrations. All right, so we said we want accurate data. We want to do light elements. We want to do fluorine, oxygen, nitrogen, carbon. These are tricky things to do, but they can be done with a WDS detector. You can see these lines. Boron and tourmaline is always going to be tricky. You can do it. You can get down to beryllium in some cases, although not really. And then with a new type of spectrometer, you can actually at least see lithium. So for light elements, the probe is the way to go, just because of the way the spectrometers work. I'll explain that in a second. And we saw that when we're looking at that phosphorus mineral on the SEM, we saw how all those rare earth lines are really crunched in together. The resolution, the spectral resolution of the probe is an order of magnitude better than the SEM. What does that mean? It means that if two X-ray lines are close to one another, their separation, their measurability is much, much better in the microprobe. And I'll show you a classic example of that. Just before I start on that though, why is a microprobe different from an SEM? There's a couple of reasons. As I said, it's built for qualitative analysis. It's got a different type of spectrometer called a wavelength dispersive spectrometer. And I'll show you the next picture here. So this top part here is the same as our standard SEM. Down here is our WDS spectrometer. And this is a WDS spectrometer here. And you heard of Bragg's law last week. WDS spectrometers work via the action of Bragg's law. These spectrometers are tunable. So here's the sample here. The electron beam is coming down. We're generating our X-rays. We have a diffracting crystal here. The crystal has got a known despacing. Okay, the crystal planes are known. The spacing between crystal planes are known and are exact. And we've got a detector down here. And what we do is we set up this spectrometer such that only the X-ray we're interested in will solve Bragg's law on that diffracting crystal and diffract crystals into that detector. So very, very sensitive to small changes in X-ray wavelengths. Okay, so we can be very selective at the X-rays we do. These, as I said, these are tunable. This is the motor here, so we can change the position of this crystal and the detector to get different wavelengths in that spectrometer or in that detector. And why are these spectrometers better? This shows it all in one shot. This is a mineral called bonitoite. Bonitoite is a barium titanium silicate. And one of the real pathological interferences in X-ray lines is between barium L-alpha and titanium K-alpha. Okay, there's two lines. And if you look at it in the EDS, you can see this lower line here, okay? That hump, that single hump. That is the two lines together. And we have no hope of separating those lines. So if we wanted to analyze a bonitoite sample, we couldn't use EDF because EDS just can't tell us how much barium or titanium is there because we can't resolve the separate lines. If we look at the other profile here, these two lines are from the microprobe, the scanning the microprobe. And we scanned X-rays and we've made a spectra of that part of the spectrum. And you can see we can very easily separate the barium lines and the titanium lines on that spectrum. And again, more pairs here. We have L-alpha 1, L-beta 1, so we got more lines. And we can separate those lines with the WDS spectrometer and not the EDS. Okay, so very tricky. This situation, and I'll show you in a second, gets really, really bad when you have rare earth elements because rare earth elements almost always show up as a clump, and because they're very similar to one another, the X-ray lines are always very close together. One other thing I wanted to show you about this is the peak, what we call the peak to background ratio for each of these. EDS peak to background, so the height of the peak of this line over the background is quite low compared to the peak to the background for these WDS lines. And better peak to background means better detection limits, okay? So detection limits in the probe, if I'm not paying too much attention, if I'm not really concerned too much about detection limits, 500 ppm, 1000 ppm, very doable, not much of a problem at all. If I really, really work hard at looking at things like, there's a thermometer, one of the students here used the amount of titanium in quartz. And very special, I don't think I'll ever do it again, but you can go down to 7 parts per million titanium in quartz. You can do, I didn't believe it myself, but I could reliably do it, and I can measure 0 in my blank. So I am getting down to about 10, 15 parts per million titanium in quartz. That's really pushing it, and that took more preparation time than the actual analysis time. And just for reference, this is the EDS spectrum I'm telling you about. This is a monazite, and so you can see lanthanum, cerium, promethium, neodymium, samarium, gadolinium, and europium, all there. And all those lines are very tight together. And on the WDS, we can easily separate those lines. We still have to correct a bit, but we can easily separate those lines. And this is where the WDS is much superior to EDS. All right. So, what's involved with WDS? It's not as simple as putting a sample in the machine. Okay, I'm going to go about 5 more minutes and I'll answer questions as long as people have questions. It's not like EDS, you put the sample in, put the beam on it, and you measure the X-rays coming off. I have to do a lot of prep work, a lot of exploratory work, figuring out how I'm actually going to measure to get proper results. Like any analytical equipment, garbage in, garbage out. So you really got to know, prepare in advance how your sample is going to be measured. I need to know what kind of beam energy I need. I need to know what kind of beam current I need, how many electrons I'm going to put in. I need to know which X-ray lines I'm going to measure, and I need to know if one X-ray line is going to interfere with another. So even if I don't pay attention, even if I'm looking at a pure titanium sample, I will still, the detector will still say it's seeing some X-ray counts. So you have to account for things like that. Counting time, how much precision do you need? How much what kind of detectability limit you need. So all of this takes work. And then WDS is also standardized. So I'm analyzing let's just say a force rate, very simple system. What I will do is I will have a force rate standard, which is a piece of force rate and I know the exact composition of. And I will measure magnesium on that and silicon, for example, and find out how many counts per second I get for that given amount of magnesium or silicon. That's my standard. And then I go to my unknown, measure magnesium and silicon again, and compare and make those two a ratio. And after some really serious matrix corrections, because we have to do corrections. It's not just proportional to the number of counts. And I'm not going to bother getting into it, but I've taken an entire week's course to do that and to do one calculation, just so we know how to do it. So and I've never done one again. It's computerized now, but it's a lot of physics and a lot of X-ray physics and things like that involved in actually calculating how you turn that counts per second on your unknown into an actual weight percent. Okay, so here's some real data. This is, again, one of those, this is a mangano-colloidite grain, and this is a backscatter image. And we know from backscatter that the higher the average atomic number of something, the brighter it is. So in mangano-colloidite, we have titanium and niobium in the same site. And they replace one another. They have an actual one-for-one replacement in terms of atoms. So I know in this part here, the very bright part, that's the tantalum-rich end of that crystal. And as we go farther and farther, we can see the zoning. And the zoning is mainly variability in the amount of tantalum or colloidite, or niobium in one particular area. So I just did a profile of this. Okay. I did the 15, 20 points. And then, I don't know if you can see that, probably can. All these dots here are just average analyses from all of the colloidanites that I've analyzed. But this particular one, you can see the bluer dots here forming this range, and that's the zoning in that crystal. So you can see the variability in manganese and iron and tantalum and niobium in that crystal. So let's just take a look at one analysis. So what are we looking at? We're looking at one particular data point for microprobe analysis. And how do we assess the quality of this? One of the quickest ways to do it, especially in a phase that's got no water or any other non-volatile element, is look at the total. And I would like to see a total if I'm measuring all the elements in there between 99 and 101. And so this one's slightly over, it's 101.1. I should have picked a better analysis. But again, I'm not worrying about that because the real characteristic you look at to tell if an analysis is good is does it make a good crystal formula? So the formula for colloidite tantalite minerals is, in this case, the mangano-colloidite, is MnTA2O6. Quite a simple formula, okay? But in the manganese site, we can also get iron, and in the niobium site, we can also get titanium. So let's look at that. So if we look at, in terms of formulas, I calculated how many atoms of manganese, iron, tantalum, and niobium we get if we had 6 atoms of oxygen. So for manganese, we get 0.74 atoms and 0.26 of iron. So that adds up to exactly 1. So that is exactly what we want to get for that site. We have one site completely filled by iron and manganese. And then the tantalum and niobium 1.58, tantalum 0.4. So that's only 1.98, and that's a significant loss. We should be at 2 atoms. But if we look farther down the list, we can see that we got 0.02 atoms of titanium, which does fit in that site. So that site is now a total of 2. So that is a good stoichiometry. Obviously, it can get a lot more complicated, and things like amphiboles and stuff like that, you don't calculate it by hand. You need you can get software to do it and things like that. But that's the main thing. We look at the fit of our chemical analysis of our formula to see how good that analysis is. If we can make a good chemical formula, we're probably heading in the right direction for that. What else do we want to look at in this analysis? look at detection limits, okay? So all those detection limits, average detection limits in that list are between 400 ppm and 800 ppm. So reasonable. And one of the things we see above is we get 2000 ppm tin, not unusual. We get a little bit of titanium, 0.38. Scandium comes in at 0.03. That's 300 ppm, but that's below detection limits, so that could be just X-ray noise. So that I don't really count that. What do we have that's real? We've got some hafnium. Hafnium, this is on the edge, but the detection limit for hafnium is 400 ppm, and we've got about 600 ppm hafnium. So that would suggest to me that there is some real hafnium in there. The error on the hafnium, which we calculate, is about 31%. Okay, so it's a fairly large error. If I was really interested in hafnium, I would count longer on that to lower that error. So this is what we look at for doing microprobe analysis. And again, this is a nice simple analysis to do. One last thing. So one of the neat things we can do with these new automated machines is we can do what's called quantitative X-ray maps. So this is the same grain again. And what I did is I set up a 400 by 400 grid with each pixel 1 micron apart. And each of those pixels, I did a full quantitative analysis over 200 milliseconds. So 200 milliseconds per pixel, very short time. But I can actually do a full quantitative analysis for each of those pixels. And so now what I end up with is this map here. In this case, this is a map of niobium in that crystal, okay? And you can see the brightness in here now is not a function of backscatter. The brightness is a function of the actual quantitative amount of niobium in that crystal. So I just did a profile here, and you can see that niobium in blue here is actually completely antithetic to tantalum in red there. So this is really good for looking at patterns in minerals, seeing how they change as they grow, to see how the zoning works. And an interesting thing that this map showed me that I didn't quite get, wouldn't get from rare analyses, is that the titanium here actually shows up more in tantalum-rich zones. So titanium and tantalum, which is not surprising, show up together in the sample. All right, that's all I got. It was a lot. Thanks for your patience. Anybody have any questions? I'll take questions for a bit. Oh, only 3 people left. All right. Let's see. Yeah. Paul says there's a delay here, so we'll give a few minutes for questions. If not, then I'll thank you all for attending your attention. And if you have any questions that you don't want to do in public, just send me an email. It's gpoirier@nature.ca. Okay. I guess everybody's got it also. Very weird giving a talk to nobody. I know you're all out there. Thanks for paying attention, but the lack of feedback. All right, no questions. That's always a bit disturbing. Either I did it perfectly and everybody understands exactly what I said, or more likely you're all absorbing it, which is fine. Thanks again for your attention. I really appreciate. I like talking about microscopes and stuff like that. So enjoy and happy collecting. Oh, hang on. Oops. Shit. I got a few questions. I don't know if can people still hear me? Can somebody just let me know if they can still hear me? And I will answer the questions. Okay, sorry. I didn't see that the questions had slid off down the back of the thing. Okay. So Ray, yeah, to get our true ineffable species name, you pretty much need pro. I mean, some of them actually sometimes you can tell by the shape and stuff like that. But gold standard pretty much is microprobe. EDS probably could do it in a lot of cases, but yeah, there's a lot of funky things you need to do with stoichiometry, and probe is typically the way to do it. But like I say, not always. You can sometimes, obviously, you can tell by features and stuff like that. You can get a pretty good idea what the name is. But to get a name in the sense of the International Mineralogical Association, yeah, you need a microprobe analysis. Analysis, Liz. Analysis depends on what you want. EDS analysis, 15, 20 seconds. On a probe, depends on what I'm analyzing. If I'm analyzing, say, a feldspar, I can do an analysis in 2 minutes. If I'm analyzing something that's got all the rare earths in it, say, and I need to analyze all those rare earths, analysis can take 30 minutes. So it depends on what you're doing, and again, it depends on how much accuracy you need and what your detection limits you need to have. Back next week. I think Paul is giving one next week. I'm not. Specimen prep, EDS, as you saw, you can take it off the outcrop and chuck it in the machine. For probe sample prep, I've got actually polishing, mountain epoxy and polishing. So, epoxy setting takes about 8-9 hours. Polishing takes me 3 or 4 minutes, and then I got to carbon coat it, so that's another hour or so. So it's, for a probe, it can be an intensive process and take a while. Carl asked how often elements and devices have to be replaced. I'm not quite sure what you mean by that, Carl. The filaments are about the only items in the machines that have to replace. The electron sources need to be replaced. Depends on the machine. For the SEM, every 40, 50 hours. For the microprobe, better vacuum, so every 3,000 hours. I hope that's what you mean. Okay, yeah, I understand the delays with 60 seconds. Brad wants to know if you get results in mole percent for the unknown. Of course, that's just a simple calculation. So yeah, we can turn the output into mole percents very easily. It's just a question of doing some chemical calculations. All right, well, I hope you all enjoyed that. Thanks again for your attention, and happy collecting again. Thanks.